we're about to go over some practice problems for an upcoming exam. And now, let's be clear, when we talk about practice problems, these are not the problems on the exam. Some are similar, some are different, some are very different. So why do we do it? Well, we're doing practice to get used to the methods. So the ideas that we'll talk about, those are what are important. And so we're going to go through the ideas, the important things that you need, and practice. Practice is how we get better. And so as you're thinking about the upcoming exam, these are great problems to do, but not the only ones. Make sure you do a variety of problems and that you understand the ideas. Ideas are what will carry you through. Now, this upcoming exam has a formula sheet, and I have a copy of it here. And I want to point out a couple of things on the formula sheet specific to this exam. Now, we're talking about techniques of integration, and so there are three things which we should highlight. The first thing, this nice little formula here, that deals with the integration by parts. And so that's a very common technique, and it's a useful skill to have. We also have right underneath it the guidelines for how to do trig substitution, and to the side over here we have numerical integration. Specifically, information about the trapezoid rule, information about Simpson's rule, and just to be clear, because some people have asked, those are not minus signs, those are dashes, those are coefficients, and we'll probably have at least one problem where we talk about numerical integration at some point. Now, beyond that, of course, there's other things we should know. We should know our trig identities because, yes, trigonometry plays a big role in integration. We have integrals that involve trigonometry. We have problems that are algebra, which become trigonometry. We need to know how to work with trigonometry. And in particular, you have your Pythagorean identities and your power reduction identities. They play huge roles. You, of course, need to know your integrals and basic derivatives, and so those are very conveniently located. You also need to know things from the last exam, which we talked about. Yes, applications. So know how to do applications. Remember, you don't have to memorize the formulas. They're right there. And we've been through this before, and so they should be somewhat familiar. Now, there's one more thing. There's kind of like a special hidden bonus that we sometimes don't draw attention to. And it's kind of obscure. It's kind of a prelude of what's coming. And so it's not technically us, but there's this little piece down here. I just want to say it kind of will feel familiar. That says, well, the sum of 1 over n to the p converges only when p is greater than 1. Well, sums and integrals are connected to each other. And so it turns out there's another statement. The integral from, say, 1 to infinity of 1 over x to p converges only when p is greater than 1. And that can be very useful when we're talking about improper integrals. All right, so that's the layout of all the things that we might see. And there's a lot of things that we could see. So we need to do some practice. So let's get going. For what values of a and b will the integral of e to the ax sine bx dx equal 4 over 25 e to the ax sine bx minus 3 over 25 e to the ax cosine bx plus c? All right, so we're almost given the integral. We have these coefficients, but what are a and b? And we have some options here. Now, there's sort of two ways to approach this problem, so we'll do it in two different ways. Now, one way is to do it sort of with a integration mindset, but there's also a differentiation mindset that can be employed. And keep in mind that we're getting to the part of math where math is fun. It's a choose your own adventure. And so some problems have multiple ways that they can be solved. It's not a defect, it's a feature. And so when you're looking at problems, don't try to I only have one thing that could possibly work. What's the right one to pick? Think of it as, what are my options? Now, sometimes you have a very narrow set of options, but sometimes there's more than one option. And choose the one that works for you. Okay, so what's our integration mindset technique? Well, let's actually integrate e to the ax sine bx. Now, this is a classic integral problem. And it's a classic because it's an example of when we do integration by parts, and we have this kind of cyclic thing going on. And so if you ever see a combination of the exponential function with sine or the exponential function with cosine, what we're about to do is something you're going to see again. All right, so here we go. Classic integration by parts. And you kind of tell it's integration by parts because you're mixing two different kinds of things. I like to think of there's like algebra things, there's trig things, there's exponential things. And if you mix two of them together, and there's not some sort of substitution, it's usually a sign that we're doing integration by parts, and because we're mixing our exponential and trig. Okay, here we go. Now, what should be u? What should be dv? In this case, dealer's choice. And, what do I like to integrate? E to the ax is very easy to integrate. So I'm going to make that be the dv, so that's the part I'm going to integrate. And so that means that the part I'll differentiate will be the sine. Okay, well, let's see what we have. Integral of e to the ax, 1 over a, e to the ax. Easy to integrate. Don't forget to account for the coefficients on the inside. It's essentially like a chain rule, kind of in reverse, because it's what it is. It's really accounting for substitution. Okay, now the derivative of sine. Well, what's that? Well, it's cosine. Don't forget to pull out that b. So chain rule, b cosine bx dx. Okay, so this becomes, by integration by parts, uv 1 over a e to the ax sine of bx. And then minus integral v du. And, notice that when we multiply, we have some constants here. I'll go ahead and pull the constants out in front. V over a integral, and we're going to have e to the ax cosine bx dx. Okay, good. Now, remember, we've already sort of mentioned this is a super special case where it's like, integration by parts, the idea is so nice, we'll do it twice. And so here we go, round 2. Now we say, well, which choices should we make here? Well, it's actually kind of forced on us. Once you make a choice at the beginning, you need to be consistent. If you change your mind, you're undoing the work you did. So we're not going to change our mind. So if we use the dv for the exponential part, it stays the exponential part. If we used u for the trig part, it stays the trig part. All right, so what do we have? Well, v is again 1 over a e to the ax. And now the derivative here, derivative of cosine is minus sine. Don't forget put that b term on the inside. So minus b sine bx. All right, so what do we have? Well, we do some copying. 1 over a e to the ax sine bx minus b over a, parenthesis, use parentheses. They save points. We love our points. We want all our points. Okay, parentheses, we have our uv, so that's 1 over a e to the ax cosine bx minus the integral of v du. Now notice minus, and there's a minus here, so minus minus makes a plus. We can pull out a b over a again, and then we have the integral of e to the ax sine of bx dx. Oh, I'm barely fitting on the page, but there we go. All right, I barely squeezed it in. Okay, now let's rewrite this. And we're going to take advantage. Why did we do our parentheses? It's for right now. Because this minus b over a, it's not just going to go to that first term. It's also going to go to that second term. And if you're not careful, that's where you often forget it. So that's why you use your parentheses. Be careful. Be the right amount of careful. And what do we have? Well, we get 1 over a, e to the ax sine of bx, and then minus b over a times 1 over a minus b over a squared, e to the ax cosine bx, and then minus b squared over a squared integral e to the ax sine of bx dx. Now here's the great thing. We got where we started. Now you're like, oh, that's terrible. But actually, we didn't quite get what we started with. We have a slightly different coefficient. So we can move things around. So we can move this to the other side. And if we do that, so we can think of it as there's a coefficient of 1 here. So there's a coefficient of 1 and a coefficient of b squared over a squared, right? It'll come across as a plus b squared over a squared. So we have that 1 plus b squared over a squared integral e to the ax sine of bx dx is equal to 1 over a e to the ax sine bx minus b over a squared e to the ax cosine bx, and there will be a plus c. Now you might say, where did that plus c miraculously appear from? And I could say, well, I just know I need one for the answer, but that's technically not where it came from. The reason we actually have it is that these two integrals are technically not quite the same. Because remember, when we write an antiderivative, it's only true up to plus c. And so that's why we said, we're going to put these together and treat them the same, but they're actually off by a constant. So that's what that's accounting for. All right, now our last sort of big idea before we get into our solve for a and b is we say, move this across. And so how do we do it? Well, if you look, this is a squared over a squared plus b squared over a squared. So it's a squared plus b squared over a squared. So multiply everything by a squared over a squared plus b squared. And we come to the conclusion that the integral of e to the ax sine of bx dx is equal to, in the first case, an a cancels. So we get a over a squared plus b squared e to the ax sine of bx. And then we're going to get minus, and here the a squareds cancel, so minus b over a squared plus b squared e to the ax cosine bx, and the c absorbs the constant. That's the nice thing about constants, is you can absorb. And we say, aha, ho, ho, ha, ha. We make all sorts of happy noises because we're like, hey, we see something going on. We see that this part right here, that's our 4 over 25, and that this part right here, this minus b over a squared plus b squared, is minus 3 over 25. Now, with that in place, we're like, oh, well, that's going to make it pretty quick to find. Now, you might say, oh, I see that, but be careful. Be careful. That's a and b. We have that a squared plus b squared downstairs. And so what's going on here? Well, we can do one of two things. We can actually solve, or we can just quickly test. Well, we say, okay, well, look, this has to give me 4 over 25. Those will be negative, so those won't work. That'll give me 3 over 9 plus 16. Okay, that's not going to work. That'll give me 4 over 9 plus 16. That is 4 over 25. Okay, how about here? I'll get minus 3 over 9 plus 16, which is minus 3 over 25. That does work, so D is valid. And you might say, well, wait, hold on. What about these two options here? Will those work? No. So what happens is when you square a squared, you get 16 over 625. And here this becomes 9 over 625, which becomes 25 over 625, which becomes a number, 25 over 625. That's 1 over 25. So that's what a squared. Oh, wait, no, sorry. I can do math in my head. All right, let me say this again. 4 squared, 16. 25 squared is 625. 3 squared is 9 over 25 squared, 625. And that would combine together to give you 25 over 625. And, all right, well, you can cancel a factor of 25, so that would give you a 1/25 downstairs. And now, if you were to divide, 4 over 25 divided by 1 over 25 would give you 4. That's not what we have here. We want 4 over 25. So E doesn't work. It looks like it does work, but it doesn't work. Okay. Whew. Now, you might say, well, wait. Why don't you just go ahead and finish solving it here? Okay, we can do that. We can do that. Let's try that. Let's see if we can't solve it without plugging in. But keep in mind that when you're doing multiple choice, you can just plug in. So why not do it? Well, what do we have? Let's see. Can we fit it in downstairs? We get that a over a squared plus b squared is equal to 4 over 25. And we get that minus b over a squared plus b squared is equal to minus 3 over 25. And now we can move things around. So we get that a divided by 4. I'm moving the 4 across. That's a squared plus b squared over 25. Okay, all right, just swap, swap, swap. And on the other hand, I can move this minus 3 across, and we get that b divided by 3 is equal to a squared plus b squared over 25. Yes? Yes. And so we get that. A over 4 is equal to a squared plus b squared over 25, which equals b over 3. And now that tells us, aha, that a is 4/3 b. And now, what can you do? Well, you can take that information and you can plug it in to either formula, and that gives you one single equation in terms of a and or b. And now, once you have that equation, you can solve. And if you can solve it, then you're done. All right, so I won't go through and follow the steps, but that is how you could do it, and because we're running out of space here. All right, good, good. Now, I said there were 2 ways to do this problem. This is just one of them. So let me grab another copy. Let's see if we get to the same answer. Okay, so here's another copy of the problem. And, all right. For what values of a and b will the integral of e to the ax sine of bx dx be equal to 4 over 25 e to the ax sine bx minus 3 over 25 e to the ax cosine bx plus c? Okay, so now take derivatives, right? We talked about, oh, hey, let's integrate and let's see how these coefficients relate to a and b, and then we can figure out what choice of a and b works. Beautiful way to do it. We can also take a derivative and see, well, what happens? And so if we take a derivative of everything, what will happen? Well, the nice thing is the derivative of the antiderivative gets us back to where we start. So we have that e to the ax sine of bx is equal to 4 over 25, and now product rule. So derivative of the first, a e to the ax sine of bx, and then derivative of the first times the second, plus the first times the derivative of the second. Well, the derivative of sine is cosine. So, and then it'll be cosine bx times b. So it'll be b e to the ax cosine bx. All right. Then we have minus 3 over 25, and same process. Derivative of the first times the second, so a e to the ax cosine bx. And then we have Derivative of cosine is negative sine. We pull out a b. So minus b e to the ax sine of bx. All right. Well, let's gather. We have some places which have both e to the ax and sine, two of them, and we'll put those together. So we have these two pieces here. So we get 4a over 25, and then plus 3b over 25 e to the ax sine of bx. And, well, same thing, but now with the cosines. Well, we have a cosine term there, cosine terms there. So we have plus, we'll have a 4b and a minus 3a over 25 e to the ax cosine bx. And now our great aha is, well, wait a second, this has to match that. So that tells us that this term here better be equal to 1, and this term here best be equal to 0. So we get the pair of equations 4a plus 3b divided by 25 equals 1. So 4a plus 3b has to equal 25. And here, 4b minus 3a divided by 25 equals 0, which can be written as minus 3a plus 4b equals 0. Two equations, two unknowns we can solve, or we can just start checking. We say, okay, let's just quickly run through our cases. Minus 16 plus 9, that's not 25. Minus 12 plus 12, that's not 25. Here's 12 plus 12, nope. 16 plus 9, yes. 16 plus 9 does indeed work. And here, it'd be 16 over 25 plus 9 over 25, which would be 1. That's not 25. So D is the answer. But again, here you can do two equations, two unknowns, but we don't need to do more work than we need to. And sometimes once we can get to a point where it's like, all right, can we just quickly check our answer and see which one works? That's enough. That's enough. And you'll notice in both cases, we got the same answer. And you might think, hey, why did you show us a longer way first? There was this really short way to do it. Well, on this problem, yeah, we had a short way, but the long way might be something which can work in other cases. So for instance, we took advantage of the fact that we had an indefinite integral. If I had a definite integral, derivatives are hopeless. They can't help us at all with that. And then we would need to be able to say, oh yeah, okay, do integration by parts twice and do our rearranging. And so just, it's good to know all the options available. Now, lest anybody accuse me of saying Steve doesn't like two equations, two unknowns, I will say here's how you would finish it up. Let's suppose we want to get rid of the a. I look at this and say I want to get the coefficients in a to cancel. I can do it by timesing the first equation by 3, second equation by 4. 12a minus 12a is 0. 9b plus 16b is 25b. And 3 times 25 is 75. And that gives us that b equals 3. And once you have that, we get that 3a equals 4b equals 4 times 3 is 12, which says a equals 4. So you can, as I said, if you don't like the idea, like, no, I got to work it all the way out until I even look at the answers, okay, you can do that too. But you don't have so much time. Use your time wisely. And when we're not grading you for whether or not, you did every step on the multiple choice, we just want you to know you have the right answer. It's not the worst thing in the world to say, hey, let me step back and take advantage of that. Let me do just enough to know I have the right answer. All right. Well, one problem down. Don't worry, they won't all take this long. We will finish. We're asked, integral of 16 sine squared t cosine to the fourth t dt is equal to, and then we have these 5 integrals. Now notice, we have an integral, and we have these other integrals. So this isn't really about integration. So what's this problem about? Well, notice here we have powers, sine to the power 2, cosine to the power 4. Here, we don't have quite as much, and you'll see we don't have a way to directly integrate that. But each one of these could be integrated. You know, the ones, yeah, no problem. Cosines, great, we can do that. And cosine squared times sine, or sine squared times cosine, all of those can be integrated. So what's being tested? We're asked to rewrite this integral. And so we're like, oh, okay, so we need to rewrite. And in particular, rewrite with what? So we'll rewrite with power reduction. And so you'll notice that this type of integral is a case where we have sines and cosines to even powers. Sine to the power 2, cosine to the power 4. So when you have that happen, how do you actually integrate that? Well, you got to get the powers down. So there are 3 power reduction formulas. And you might say, well, wait a second, I have my formula sheet. There's 2 right there, right? The cosine squared is a half 1 plus cosine 2 theta. Sine squared is a half 1 minus cosine 2 theta. Where's your third? It's just up above it. Sine times cosine. So let me write them down for reference here as we go through it. So our well-known ones are cosine squared is 1/2 1 plus cosine 2 theta. Our sine squared is 1/2 1 minus cosine 2 theta. And the last one is that cosine theta sine theta is 1/2 times sine 2 theta. All right, so there we go. Those are our 3 power reduction formulas. And these are the ones that we're going to use to rewrite. Now, while they're all useful, one of them is a little bit more useful than the others. I strongly advise to use that one as much as possible. And you might say, well, why? Well, what does this have going for it that these don't? There's no plus or minus here. It's a single term. And that makes it easier to work with. It makes it easier to manipulate and rewrite expressions. So here's what we're going to do. We're going to say, well, how much can I use it? I can combine 2 of my sines with 2 of my cosines. And so I'll use it twice in essence. And I'll have a cosine squared left over because I have 2 cosines left. So I can use that. All right, to be more precise, let's think of what we have here. So we have an integral. We have our 16. And now I'm going to think of it as sine t cosine t quantity squared times cosine squared t. All right, so just emphasizing how we're going to use this. So this becomes our integral. We have 16. The sine t cosine t becomes 1/2 sine 2t squared. This cosine squared becomes 1/2 1 plus cosine 2t and dt. All right, well, we got a lot of halves here. We have a half, and there's 2 halves here. And so a half makes an 1/8 times 16. That gives us 2. So we currently have the integral of 2 sine squared of 2t and times 1 plus cosine of 2t. All right, and now we check. That's not any of our options. But we're not done yet. Let's distribute. So we're going to go ahead and we're going to take our 2 sine squared 2t and multiply that through. And what do we have? Well, we have the integral of 2 sine squared of 2t plus 2 sine squared of 2t cosine 2t dt. Now, this part does look promising, because if we look, we see that 3 of the options here have a 2 sine squared 2t cosine 2t. And if we're to believe it, it looks like we're probably going to end up with C or D. This one has a minus. These have cosine squared 2t sine 2t. That's not what we have. So right now, I'm going to guess C or D. But, okay, this part we can integrate. This part we can't. So what do? Power reduction, round 2. All right, well, what's that going to be? Okay, so sine squared, we're going to have a factor of a half. Okay, so that's integral to 1/2 1 minus cosine of double this angle, double 2t, makes 4t. Okay, plus our 2 sine squared 2t cosine 2t. And now we say, aha, 2 times 1/2, that's 1. So we have a 1. That's good. We wanted a 1. And we have a cosine 4t with a minus. And now we say, oh, yeah, let's just rewrite it. So we put the 1 in front. We'll put this 2 sine squared of 2t cosine of 2t in the middle. And this minus cosine 4t on the end. And now we're like, cool. What does it match? Okay, the ones match. 2 plus 2 sine squared 2t cosine 2t matches C and D minus cosine 4t. That means our answer is D. All right, so notice this is kind of a problem about integration, but what we're really testing on is, do you know the process of rewriting the integral? And in some sense, when it comes to doing techniques of integration, most of the work is not the actual integration. It's getting to the point where it's like, hey, now can you do the integral? And so that's what's being tested here. So be ready. We may not give you a lot of integrals to do, but we definitely will say, can you prepare? Can you take a step? Can you rewrite? Can you simplify? So know your tools, know your identities. All right. Well, 2 down, right? Let's keep it going. Our third problem. For which one of the following integrals should you use the substitution x equals 2 secant theta? And we have 5 options here. And the 5th one is a very strange looking one. All right. Now, what do we see here? When we're looking at this substitution, we say x equals 2 secant theta. We've got a trig substitution going on. And we're like, ooh. So we're really being tested on identifying a trig sub. And we say, okay, well, what are we looking for? Now, what we can do is we can grab our formula sheet because there's some very convenient guide here. And it says, all right, suppose we're doing a substitution x equals 2 secant theta. So we can come here and we see there's this nice guideline of when you do a secant. And it says, hey, if you see something like the secant is the last one, square root of u squared minus b squared, then our substitution we should make is u equals b secant theta. Now, notice how we have x and 2. So we say, okay, so that says x equals 2 secant theta. Well, that tells us what are we looking for? We'll replace u by x and b by 2. We're looking for an x squared minus 4. So look for an x squared minus 4, ideally in a square root. Now, you'll see that we have some square roots here. This has a 4x squared minus 1. That's not x squared minus 4. This has an x squared minus 4 inside a square root, because you see how that 7 halves? That's really to the 1/2 to the 7th. So that must be our answer. So we'll go ahead and circle it, but let's go ahead and talk about the rest. 4 minus x squared. It's kind of like x squared minus 4. It's not in the square root, so we're not going to worry about it. Downstairs is the square root. That's square root of x squared plus 4. Not what we're looking for. Here it's square root of 4 minus x squared. Again, not the right form. So B. Now I want to take it and say, whoa, hold on. You haven't talked about E yet. E seems really tempting. And it is really tempting. Why is E so tempting? Well, if you look at E and you say, what's the kind of substitution you'd make here? When you have things involving secants and tangents, what tends to happen is you either make a secant substitution or a tangent substitution. You're like, yeah, look, see, here's the secant substitution. Now, in this case, the substitution that would be really elegant, would work really well, would be the following. U equals 2 secant of x would be a fantastic substitution here. But compare that to the substitution we're talking about. What's the difference between these two? Because I think it's important to understand, compare and contrast. How do these look the same? How do they look different? They both involve secants. Should I say so? They're the same, right? But where does the x show up? Here, in the substitution that we're looking for, x is sort of on the outside of the secant. In this substitution, x is on the inside of the secant. So it's playing a very, very different role. So it's a very different kind of substitution. So be careful. Sometimes when you think, oh, I'm making a secant substitution, you say, well, wait a second, but how does the x show up? Is it inside a secant or is it outside a secant? Because those are very, very different scenarios. So be careful. They're going to try to tempt you. Don't be tempted. Don't be tempted. All right. But, after the last couple, this one was a pleasant one. Sometimes they're pretty quick if you know what you're doing. And, Trick's up. Beautiful idea. I'm willing to wager we're going to see that one again. Our fourth problem. We're doing the integral of x squared plus 6x plus 7 over x plus 1 times x plus 2 plus x plus 3. And we're asked what it is, and we're given 5 options. Now, there's 2 approaches you could take. If you think back to the first problem we talked about, we said, let's take the derivative of both sides, and let's see what that gives us. And it's 100% true that you could patiently take each single derivative, and fingers crossed, one of them would work. Now, in some cases, that can actually be faster than doing the problem. And if that works for you, no problem. Do it. That's a great way to solve indefinite integral problems. But sometimes the amount of work involved can be a lot. So, taking these derivatives aren't so easy, but even after you're taking the derivative, then you have to sort of rewrite it. So instead of going about it that way, we'll actually do it the way the problem has been stated. Let's do this problem. Now, what kind of problem do we have? When we look at it, we're asked to do an integral, and we say, oh, hey, there's a polynomial upstairs and a polynomial downstairs. That means that this is a wonderful partial fractions problem. So, polynomial over polynomial, channel your partial fractions. And sometimes they'll be very explicit, and they'll say, hey, here's the partial fractions form. Sometimes you've got to figure it out. But usually it's not too bad. You do a quick check with your degrees. The degree upstairs is 2. Downstairs, it's 1 plus 1 plus 1 is 3. Beautiful. You want upstairs smaller than downstairs. And we say, all right, so let's do some algebra, some partial fractions algebra. And in some sense, partial fractions really is an algebra technique. And the goal here is just rewriting what's inside our integral so that it can be more easy to work with. I guess more easy, I should have said easier. All right, so we have x plus 1, x plus 2, x plus 3. And we say, okay, well, we have an x plus 1, so partial fractions, we're going to be pulling things apart. So we say, okay, there's going to be a term for the x plus 1. We have an x plus 2, so there's going to be a term for the x plus 2. And we have an x plus 3, and so we say, okay, there's going to be a term for the x plus 3. And then there's unknowns on top, a, b, c. Now, quick sanity check. You say, okay, how many unknowns do you have? 3. What's the degree downstairs? 3. Good. If the number of unknowns does not match the degree, mistakes were made in the setup. All right, well, but now that we have that, what comes next? Clear your denominators. As I like to say, look, fractions are dangerous. I've lost too many points to fractions. So I'm going to multiply by x plus 1 times x plus 2 times x plus 3. So in other words, multiply by the original denominator. And when we do that, we get x squared plus 6x plus 7 equals a. The x plus 1 terms cancel. X plus 2, x plus 3, plus b. The x plus 2's cancel. X plus 1, x plus 3. And then don't have enough space, so I'll go to the next line, plus c. The x plus 3's cancel. X plus 1, x plus 2. Okay, well, now we have polynomial equals polynomial. You can do two things. You can plug in x values and just plug a couple of x values. Gets you a system of equations, and make good choices when you plug in your x values. The other thing is you can expand and compare coefficients. I always like to start with making good choices. What are good choices? Things that make zeros. So in other words, think about what could make zeros in these pieces. You say, well, x equals negative 1 can make a 0. Okay. 1 minus 6 plus 7 equals, here we have a times 1 times 2, and then b times 0, c times 0. Well, that tells us that 2a is equal to 8 minus 6 is 2. That says a is 1. All right, how about x equals negative 2? Because that makes the x plus 2 0. Well, all right, that gives us 4 minus 12 plus 7. Yes? Right? Now, what is that? Well, that's going to be equal to a times 0. All right, that goes away. B times minus 1 times 1. Oh, okay, well, that's convenient. And then c times 0. Okay, so minus b is equal to 11 minus 12 is negative 1. So, okay, so b is 1. And then x equals minus 3. What happens? Well, we get 9. And then we have minus 18. And a plus 7. Okay, equals 0, because there's that minus 3 will make that 0. 0 again, because again, minus 3 makes that 0. And then we have c, and minus 3 plus 1 is minus 2. And minus 3 plus 2 is minus 1. All right, so 2c equals 16 minus 18 is negative 2. Oh, so c is negative 1. Okay, now here is the classic mistake that people make when solving partial fractions problem. They actually do a great job of the setup. They do a pretty good job of solving, and then they forget to put the right numbers in the right place. So make sure you get the right numbers in the right place. So a is 1. So this is 1. B is 1. So this is 1. And c is negative 1. So this is negative 1. Which is to say the following. All this work has been to get us to say, you know, this integral is really the integral of 1 over x plus 1 plus 1 over x plus 2 minus 1 over x plus 3. And once you pull things apart, you have an integral that you can work with. So this becomes natural log x plus 1 plus natural log x plus 2 minus natural log of x plus 3, toss in a plus c for good measure. All right, now at this point, we're almost there. Just channel your inner properties of logs. Addition means multiplication. Subtraction, division. Okay, so addition, the terms that are being added, they go upstairs. The terms being subtracted go downstairs. And all our coefficients are 1. If you had any coefficients, they'd come in as powers. We don't have any powers here. And so we have log. There's an x plus 1 upstairs. There's an x plus 2 upstairs. And there's going to be an x plus 3 downstairs. And that's all our log terms. So that's what we're looking for. X plus 1 upstairs, x plus 2 upstairs, x plus 3 downstairs. We don't have to look far. Our answer is A. All right, so for reference, I'm going to go ahead and write these rules down because they're not on the formula sheet, but they're good to know. log A plus log B is log of A times B. Log A minus log B, that's log of A over B. And B times the natural log of A is equal to log A to the power B. So these are the rules you can use to simplify logs. And again, I think we'll see this again. This will not be our last time dealing with logs in our practice problems. But all right, good. We're making great progress. Let's keep it going. Using the trapezoid rule to approximate an integral, an estimate called t, and a corresponding error bound, e sub t, was produced. Okay, so it's not telling us what it is, but it's saying there was an estimate made and an error bound was found, and they're numbers. Combining these, it can be concluded that the actual integral is between 16 and 19. Oh, okay. What are t and et? Well, Now, what do we care about? You might say, okay, we have the integral, right? Maybe 1 and 5 will play a role. No. What are we really focusing on? We're trying to say, hey, our answer is somewhere between 16 and 19. So let's think about what this tells us. Now, normally, let's just ignore the problem and just think conceptually what all these things mean. So here I have the number line, and I make a guess. So I don't know where my guess is. I'll put it at an arbitrary point, t. Is the integral equal to t? No, an integral is there's a precise value attached to it. T is an approximation, which uses a little bit of sampling to say, hey, this is what it should approximately be. Ideally, it's not too far away, and that's the point of the error, is we're saying, hey, it's not t, but we're in the ballpark, and the question is, well, how far do you have to go? Well, the answer is you don't have to go far. Now, it could be at most et, but et could go in either direction. So you could move up or you can move down. And so now what we know is that the actual value of the integral is somewhere in this range. So between our estimate subtract the error bound or estimate adding the error bound. And we say, okay, well, notice what we have here. The integral, which is our value, is somewhere between 16 and 19. That tells us that in terms of our little simple diagram, 16 and 19 are at these points here. So, how can we find things? Well, we can think about how far apart are 16 and 19. And the answer is 3. Now, quickly, just actually say, oh, hey, I see 2 places that are 3. But wait a second, hold on. 16 and 19, is that the size of our error? Is 3 at most our error can be? No, because notice how we actually go 2 steps. So the difference from 16 to 19, we say, look, 3 has to be twice our error bound, right? Because we can go from the center either way. So we're looking for a place where our error bound is 3/2, which is 1.5. So now we skim. That's not 1.5. That's definitely not 1.5. That is. Could be C. That's not 1.5, and that's not 1.5. In fact, the error can never be negative. When we talk about error, it's the absolute value of the difference. So negative is just right out. So we automatically know our answer is C. But one other thing we can say is, where should our guess be? Our guess should be at the halfway point. So what's halfway from 16 to 19? Well, if the total distance is 3, I just have to go 1.5. And 16 plus 1.5 is indeed 17.5. And so that tells us that the estimate that was produced was 17.5. The error bound that was produced is 1.5. So what's going on here? What's being tested? Well, what's being tested is to understand how error works. That's actually really important. Because a lot of people are just like, a guess is a guess is a guess, and all guesses are equally important. This says, well, wait, how does error fit in? We want to make sure we understand what is our guess telling us? How much are we learning from it? A good guess, small error. Bad guess, big error. And so this is making sure we understand what the error bound represents, which is a very useful thing. All right, another one that once you understand the concepts, it's pretty quick. If you don't understand the concepts, you probably would be tempted to guess, I think A looks very tempting. Like, well, okay, 16 up to 19, so maybe our guess was 16 and our error is at most 3. But that's not how error works. And so make sure you understand ideas. It's not just numbers. It's not just formulas. Ideas. Ideas are so, so valuable. And the ability to understand and think and reason. Beautiful. I cannot recommend those things enough. All right, well, let's just keep going. We're on a roll. Let's keep it up. Number 6. Woohoo! Our final multiple choice problem. And looks interesting. So which of the following improper integrals converges? And so we have 5 improper integrals. And why are they improper? Well, all of them involve infinity in their bounds. And you might say, okay, well, that's definitely a reason. Is there anything else we should worry about? Well, we maybe have a divide by 0? No, we do definitely have lots of denominators, but they're always positive values because we're going from 1 to infinity. So there's no divide by 0. So the only thing that makes it improper is the infinity bound. So, okay, well, how does one make a decision? Now, notice what we're not asked to do. We are not asked to integrate any of these, and we will not do that because that is a hopeless problem, and we do not have time. We would be here for months, and even then, we probably would be like, any ideas? I don't have any ideas. So we're not doing that. We're not actually going to integrate, but we're going to make decisions. So how do we make decisions? Well, there's going to be 2 beautiful ideas that we're going to bring together. The first thing is we say, well, do we know some sort of group of improper integrals where we can definitively say yay or nay? And there's a very special one. All right, so here we go. So the key one we're going to work with, the integral 1 to infinity of 1 over x to the p dx converges if and only if, so that's pretty strong, p is greater than 1. So if p is greater than 1, it definitely converges. And if it converges, it must be the case that p is greater than 1. All right, so that's going to be one of our 2 keys. And then you look and say, you don't have any of those options, Steve. And now, we do have one other beautiful idea. So we're going to take this idea and we're going to add in what I like to call the limit comparison. And limit comparison says focus on the leading terms. So what does that really tell us? Well, when we're thinking about whether or not something converges or diverges, the real root of the question is how quickly does something get small? The rate of growth to 0, or maybe more precisely, the rate of decay. So it can be the case that if you get small fast enough, you'll converge. And if you don't, you'll diverge. There's this sort of delicate line. So for example, the integral of 1 over x diverges, but the integral of 1 over x squared converges. So the question is, well, how quickly do you get there? And so limit comparison says, look, ignore the noise, focus on the things that matter. What's driving the growth? What's driving the growth? Now, before we go and do it, I do want to point out one thing. This is a really useful thing to remember, and it's not explicitly stated in our formula sheet, but I do want to point out, we already mentioned this. It's kind of showing up here. See how you have this sum of 1 over n to the p converges only when p greater than 1? It's the same idea. Here, instead of sum, it's like an integral 1 over x to the p dx converges only when p greater than 1. It's not a coincidence that they look highly similar. In fact, they're tied together. It's a great story for us to tell, but if you're trying to remember it, look down here, and you're like, oh yeah, that's right. That's right. There's something about an integral here. Okay, so how does this work? And it's a really simple idea. You just say, hey, if I ever see a plus, only keep the thing which is the biggest. That's all I need. So if I see a plus anywhere, I'm only keeping the bigger thing. That's what's driving growth. And when I do that here, I'm going to be able to look at this integral and say, well, yes or no. So let's start with a. Well, I see a plus. What do I keep? From x or 3? I keep the x. Okay, so I want to look at x squared upstairs. What's downstairs? Well, x cubed worth is 1,000. Well, keep the x cubed. Square root of x cubed. And now, well, let's simplify that. That would be what? I have x squared upstairs. This would be x to 1.5 downstairs. That becomes integral x to the 0.5 upstairs. Oh, this is really hopeless. Really hopeless. And forget it. Not going to converge. Right? It's just getting bigger. It's getting bigger. All right. So, nope, not going to work. Okay, so that's A. So it's not A. Well, let's do another one. Let's try B. Okay, so let's go to B. Well, what do we have? We're looking at integral upstairs. X plus 3. Again, drop the plus 3. Only keep the thing that's the big part. Now downstairs, what do we have? Well, we have x to the 4th versus x squared versus 1. X to the 4th is the big part. So we're going to have a cubed root x to the 4th. All right, so that's what we're thinking about. And I should have said, really, we're comparing these integrals. So 1 to infinity, I'll put bounds here. So frowny face means doesn't converge, diverges. All right, so 1 to infinity of this integral. And these aren't values. These are just saying yes, finite, no, infinite. 1 to infinity, square root, that's x to the 0.5, or 1/2. Here, you'll have x to the 4/3. And, okay, maybe I'll write it as 1/2. If you take 4/3 and subtract a half, because a half is smaller than 4/3. So the good news is we are going to go to 0. What is 4/3 minus a half? Well, okay, we have to think about that. 4/3, that's like 8/6. 1/2 is like 3/6. 8/6 minus 3/6 would give us to the 5/6. All right. Well, will that converge? Well, 5/6 is not bigger than 1. This is not going to converge. B is out. All right. Do you see our game? Drop the lower order terms and say, what's your power of P? That will help us answer our question. Okay. So now, hopefully we can start picking up our game. 1 to infinity. What do we have here? Again, 9x and 18 are small compared to x squared. Then I have x squared to the 2/3. So upstairs, I have like x to the 4/3. Downstairs, x squared versus 36, the x squared wins, right? Focus on the leading terms. Not necessarily the term in the front, but the term with the biggest contribution. And so you can get rid of addition. And we love that. It makes things easier. And we say, okay, well, we would subtract 4/3. 2 is 6/3. 6/3 subtract 4/3 would leave us with a x to the 2/3 downstairs. And, well, okay, how does 2/3 relate to 1? It's smaller than 1. We're still going to diverge. All right. Well, now we're down to a 50-50 chance. We're going to do better than 50-50, though. Come on. We got to do better than 50-50. Okay, so next one up. 1 to infinity. Okay, we have our x squared versus 20x versus our 99. X squared, that drives the behavior. So x squared. That's how the top is behaving. Downstairs, we have an x cubed, a 10x, and a 21. X cubed drives the behavior. X cubed. We say, well, hey, that's like 1 to infinity of 1 over x. Oh, well, that's like p equals 1. Right on the line. Right on the line, but 1 is not bigger than 1. So it's barely going to fail. So this will also diverge. Now that means by process of elimination, our answer must be E. But, I'm not just happy to do process of elimination. Let's also see that the theory actually is coming in. And, well, what do we have? Well, we're going to have integral. And we say, okay, well, look at your powers. What dominates? X cubed versus x versus 1, the x cubed. So upstairs is x to the 3/2. Downstairs, cubed, x6, x squared, 9, the x cubed dominates. And we say, okay, well, what's x cubed versus x to 3/2? Well, subtract, and we have, this is like 1 to infinity, 1 over x to the 3/2. And now we say, well, wait, 3/2 is bigger than 1, so this will converge. And so life is good. All right, now, I don't know if I said it explicitly, but let me just do a recap here. What's going on with limit comparison? The idea with limit comparison says, I want to figure out whether or not my integral converges, so I'm going to compare something which has the same rate of growth. That's the goal. And so limit comparison says, I'm going to compare something with the same rate of growth. It will converge if and only if the simpler thing converges. So by throwing out the lower order terms, I can tell whether or not the whole thing converges. And so limit comparison says, oh yeah, whatever this simpler integral does, this integral does in terms of converge, diverge scenario. So by throwing out the lower order terms, we saw the first 4 cases all led to integrals where we did not have p greater than 1, we had p less than 1. So all 4 of these had to diverge, but the last integral we were left with an integral which would converge. So if this integral converges, this one also converges. And so that's how we got our answer. So it looks like I wrote down a lot, but once you start realizing, oh, wait a second, rates of growth, that determines behavior, that makes things a lot easier than it actually looks. And so it's some very simple ideas. It's just knowing how to put it all together, which is why we're practicing, right? The more we practice now, the better things will get. And all right, that leaves us out of the multiple choice and into the workout problems. Woohoo! Let's bring it on! Oh yeah! Number 7. Ah, nice. Okay, so we're asked to find the integral from 0 to pi over 2 theta sine cubed theta d theta. What kind of problem do we have here? Well, notice that we do have 2 things multiplying together, and they're 2 different types of things. So theta, that's an algebra type thing. Sine cubed theta, that's a trigonometry type thing. And so when you have that type of behavior, sort of a mixing of types of functions, it's usually a good sign that you should think of integration by parts. So let's suppose we put our integration by parts hat on. We say, all right, so let's do our integration by parts. Now, with that in mind, we say we need to decide what are we going to integrate, what are we going to differentiate. Now, that sometimes sounds like an easy thing, but it can be a little bit subtle. So let's think ahead and say, what's our ultimate goal? Well, our ultimate goal is to get something that we can get an answer. So we want to simplify. So we look at this algebra part and we ask ourselves, okay, do we want to integrate or differentiate? And we think to ourselves, oh, we would love to differentiate because one derivative here and it goes away. It becomes a number. So whenever you see like thetas or x's or t's, whatever your variable is called, that's a clue. It's a good clue that says, hey, you should try this to be the part that you differentiate. Will it always work? No, but it's worth a shot. So let's do that. So we're going to let u be theta, which means that dv is sine cubed theta d theta. Now, good news, one of these will be pretty quick to compute, and that's our du. du is d theta. Now what about v? Well, let's recall dv is sine cubed theta d theta. So what we want to do is, if we want to get v, we want to integrate this. So we say, well, okay, so v is the integral of sine cubed theta d theta. Now, how does one integrate sine cubed? Well, we're going to take advantage of the power. It's odd. Sine to the power 3. And 3 is an odd number. Totally true story. It is very odd. Now, when you have odd powers to sine, what you can do is you can pull off a sine to the end, and then once you pull that sine off to the end, you can deal with what's left. So in our case, we say, well, let's pull off one of our sines. So sine squared theta is sine theta d theta. And this part right here is going to become our dw. I'm not going to use u because I've already used u to mean something else. And now we say, well, okay, so we want to make a substitution. We need to rewrite the sine squared, but we have ways to do that. So this is the integral 1 minus cosine squared theta times sine theta d theta. And now we're ready. W equals cosine theta. dw equals derivative of cosine minus sine theta. And so we end up with the integral 1 minus w squared times a minus dw. And, well, okay, well, that's not so bad. Don't forget to put the minus through. So that would be minus w plus 1/3 w cubed plus c, which would make it minus cosine theta plus 1/3 cosine cubed theta plus c. Okay, so there's our v. All right, so we have u, v. Now, we don't need to use the c because we're doing a definite integral. So we get theta times minus cosine theta plus 1/3 cosine cubed theta. And it's a definite integral, so evaluate 0 to pi over 2. Minus, now we're going to do v du. Okay, so we have minus the integral from 0 to pi over 2. And then we have a minus cosine theta plus 1/3 cosine cubed theta d theta. Okay, well, let's do our evaluation. And if we plug in theta equals 0, then we get 0. If you plug in pi over 2, cosine of pi over 2 is 0, which tells us that this part is 0. Nice! And now we can distribute the minus through. So we say, oh, okay, well, this is really the integral from 0 to pi over 2 of cosine theta minus 1/3 cosine cubed theta d theta. Okay, now how do we integrate this? Well, you have a cosine cubed. And here you have cosine. So it's like, oh, you have cosines to odd powers. Let's pull it off, and then we'll do a little change. So, okay, so this is 0 to pi over 2. And we'll think of this as 1 minus 1/3 cosine squared theta times a cosine theta d theta. Now, we say, okay, what's going on? Well, we're preparing ourselves. We're getting to ourselves where we say, okay, this part is going to become our dw. So we need to rewrite everything in terms of our signs. And so we do what we did before. We say, oh, well, okay, this can become 0 to pi over 2 of 1 minus 1/3, 1 minus sine squared, and then we have our cosine theta d theta. And here, if you clean this up, 1 minus 1/3, that becomes 2/3. Then we have a plus 1/3 sine squared theta. Okay. Now, great. Go ahead and update everything. And we're almost there. We're almost there. And our next thing is we're making our substitution. W equals sine theta. dW is cosine theta d theta. And update your bounds, right? We always update our bounds so that when we go forward, we never have to go back. Sine of 0, 0. Sine of pi halves, 1. 2/3 plus 1/3 w squared dw. All right, well, that becomes 2/3 w plus 1/9 w cubed. Right, you add 1 to the power, divide by the new power, and evaluate that. 0 to 1. Plug in 0, you get 0. Plug in 1, you get 2/3 plus 1/9. Well, that's 6/9 plus 1/9 makes 7/9. And there we go. Great. So we're done. We found our answer. We wanted a number. We got a number. So what happened here? What was going on in this problem? Integration by parts, definite integral, plus we had to do a little bit of a trig integral on the side. In fact, we did sort of an integral which involved the sine cubed. We did an integral which involved the cosine cubed. But we just remembered, hey, if you have an odd power, that's pretty convenient. Just pull off one of their terms. That's going to become your d something, and then write everything in terms of the other one. So if I saw a sine to an odd power, I pulled off a sine, write everything in terms of cosine. If I saw cosine to odd powers, I pull off a cosine, write everything in terms of sine. And then life is good. Life is wonderful. We got a great answer. Great answer. All right. Well, let's keep going. Number 8. We're asked to find the integral of 2y to the power 9 times 4 plus y to the power 4 to the negative 3/2 power dy. And then we have this hint. The following might be helpful. We have the integral of secant cubed theta is 1/2 secant theta tangent theta plus 1/2 log of secant theta plus tangent theta plus c. Now, on a side note, you might say, oh, that's the integral of secant cubed, and that's not on the formula sheet. I mean, that's why it's in a hint. Should I worry about memorizing that? No. We remember, your teachers love you. They want you to succeed. You know, there's lots of warm, fuzzy feelings between math teachers and their students. And so it just says, hey, this might come up. In fact, it kind of is suggesting that perhaps we should expect it to come up in some way, shape, or form. Well, let's find out what happens. Lots of things to go. Now, looking at this, what are we thinking? We're kind of thinking trig substitution for two reasons. One, they gave us an integral involving trig, and there's no trig to begin with. So it's like, oh, we'll probably want to go to trig. But there's another thing. We see a square root. That's what this over 2 is telling us. And there's something being added or subtracted inside that square root. So we're like, ooh. When we see adding or subtracting inside square roots, we're kind of thinking trig substitution is a reasonable way to approach it. Okay, so let me rewrite this in a slightly different way. Not that it's better, but just to sort of emphasize what's going on. So we have the integral. We have 2y to the power 9. And really, what does this mean here? The minus says go downstairs. That's why I put a fraction. And to the 3/2, you can think of it as the square root of 4 plus y to the 4th cubed. So that's how we can think of that power. So it's there's a 3 there, dy. So that's what's going on. Now, when we think about trig substitution, we have to remember which one goes where. And looking at our formula sheet, we see, we see number squared plus varying thing squared. So that says, okay, the plus plus, that says we should be thinking tangent. So we say, okay, so make some notes here. The square root b squared plus u squared tells us we should make the substitution u equals b tangent theta. The b here is standing for a number. The u is standing for the varying part, something with a variable. So for us, we say, well, 4 is 2 squared. Y to the 4th is y squared squared. So 2 squared plus y squared squared. Okay, so if we just follow the recipe, u is y squared and b is 2. So y squared equals 2 tangent theta. So that is our substitution we're going to make. All right, well, let's now just go through and say, what does this tell us? What's going to happen? Well, take derivatives. 2y dy is equal to 2 derivative tangent secant squared theta d theta. All right, so that's something we'll need to deal with. Now, the good news is we have a 2. We actually have a bunch of y's upstairs, not just one y. We have 9 y's, but we'll get to that in a second. And okay, what about this square root of 4 plus y to the 4th? Well, that's going to become a square root of 4 plus 4 tangent squared theta, which is really the same thing as square root of 4 times 1 plus secant squared theta. And that's going to become a 2. And 1 plus secant squared, 1 plus tangent squared. I knew where we were going. 1 plus tangent squared is secant squared. And so that becomes secant. Okay, all right. So these are notes on the substitution. All right. Well, okay, the 2's actually end up canceling. And so we still have a 2 up there. It'll probably be helpful at some point. So we have a 2. The y dy, so we can pull a y off to the end. Now, we have 9 y's, though. That leaves us with 8 y's to deal with. How do we deal with them? Well, notice how we have a y squared. So we're going to rewrite that as y squared to the 4th. So I want to rewrite it in a way that can help me with the substitution. Divide that by, and then we have the same thing downstairs, the square root 4 plus y to the power 4 cubed. Okay, now all the pieces are in place, and it's time for us to see what goes on. Here we go. This becomes equal to the integral 2 times y squared becomes 2 tangent theta to the power 4. Square root of 4 plus y to the 4th becomes 2 secant theta to the power 3. Y dy becomes secant squared theta d theta. Okay. All right, well, we can clean up. What can we clean up? We have a lot of 2's here. There's 5 2's upstairs, 3 2's downstairs. So if we put all that together, that leaves us with 2 upstairs. So that's going to be a 4 tangent to the 4th theta. We have 3 secants downstairs and 2 secants upstairs. So that leaves us with a secant theta. And then we have a d theta. All right. So that's what we're down to. Okay. All right. What do we do? Now, there's a couple of ways to approach this, but we can start thinking about what's our goal. With tangents and secants, we have a couple of things where we're able to sort of say, oh, there's this nice identity which connects tangents and secants, which is that tangent squared plus 1 equals secant. Now, it's not a bad idea to sort of say, how can I get to my hint? You say, well, if this was like a secant to the fourth upstairs, you'd have secant to the fourth over secant, which would be a secant cubed. You'd be playing the right game. You say, well, that's good. Why don't we get to that point? Because what's our sort of mindset when it comes to tangent squareds and secant squareds? We can swap. Now, not one-to-one. It's not like, oh, tangent squared is a secant squared. But it's almost, because we have our classic identity. So here's our idea. And just to be clear, this is the identity I'm thinking about. Tangent squared plus 1 equals secant squared. Let's use that to replace the tangents in terms of secants. And let's see where that gets us. And I'm thinking of that because I want to get to secant cubed so that we can use the hint. And it'd be good to use the hint. It's like they want us to succeed. So a little bit slowly, let's get there step by step. So tangent to the fourth is tangent squared squared. And now tangent squared, well, we think of that as tangent squared is secant squared minus 1 squared. Okay, and we can expand. So this becomes 4 secant to the fourth theta minus 2 secant squared theta plus 1 over secant theta d theta. All right, good. Now, let's put the secants over each term. So we have integral secant divided by secant to the fourth, or into secant to the fourth. That gets us 4 secant cubed theta. Okay, good news. We know how to do that. How about secant squared divided by secant? Well, we're going to have 8 secant theta. Good news. We know how to do that. And then we have plus 4 over secant. Well, what do we know about 1 over secant? It's cosine. How do we know it? It's actually kind of built in right there. Secant is 1 over cosine, so cosine is 1 over secant. And so we get a plus 4 cosine theta. And now we're like, yes! Each thing we can integrate. So here we go. This equals 4 times 1/2 secant theta tangent theta plus 1/2 log secant theta plus tangent theta. Okay, so that's the first term. Minus 8. And what's the integral of secant? Well, it's in the formula sheet, but it turns out it's log secant theta plus tangent theta. And what's the integral of cosine? That's right. We saw the sign, and it opened up our eyes. We saw the sign. Nothing's going to give it up. Oh, wait, sorry. All right. Focus. Got to do the problem. It's not just about having fun. We got to do some work. All right, we're nearing the end. We have to be. We're running out of space. So 4 times 1/2 makes 2 times secant theta tangent theta. Then we have plus 2 minus 8. So that makes minus 6 log secant theta plus tangent theta. And then plus 4 sine theta and plus c. Okay. Woohoo! We integrated! Nice! Are we done? No! Wow! Come on, Steve, we're very animated. We must be close. We are close. What's left? We need to unravel now. Okay, so how are we going to do that? Well, we go back to our original substitution. we said that y squared is 2 tangent theta. Now we could solve for tangent theta, and that would become tangent of theta is equal to y squared over 2. Draw a nice triangle, or it doesn't even have to be that nice, but don't draw the wrong triangle. Draw a right triangle. Put theta in the corner. Tangent, gotta channel your inner SOHCAHTOA, right? SOHCAHTOA, where the triangle edges all have names. There's the opposite, the adjacent, and don't forget hypotenuse. All right, so tangent, what's that? That's the TOA. Opposite over adjacent. Y squared over 2. And that last side, use Pythagorean theorem. We have two sides, so we take a squared plus b squared, square root of that. 4 plus y to the 4th. Okay, so we say, great, well, what's secant? Secant is hypotenuse over adjacent. So that's the square root of 4 plus y to the 4th over 2. Tangent is opposite over adjacent, so that's y squared over 2. Minus 6 log. Okay, secant, again, hypotenuse over adjacent, square root of 4 plus y to the 4th over 2. Tangent's opposite over adjacent, so that's y squared over 2. And sine is opposite over hypotenuse. And that's the SOHCAHTOA. So opposite over hypotenuse. Y squared over the square root of 4 plus y to the 4th. And plus c. Now, cleaning it all up, at the end, what do we end up with? Now, here we can get some 2's to cancel. So we'll end up with y squared square root of 4 plus y to the 4th over 2. Here, we can actually do a little bit of a trick. Now, you don't need to do this if you don't like what I'm about to do. See how you can put it over 2? And then you can say, oh, I have a division, and then I can pull that 2 out. Yeah, you can. And so this becomes minus 6 log square root 4 plus y to the 4th plus y squared. And you might say, well, what happens to that minus 6 log 2? It gets absorbed by that plus c. And then you have plus 4y squared over the square root of 4 plus y to the 4th. And now, if you did a little bit of algebra, you could put these together. We're not going to do that. I'm just saying it theoretically could be done. It's not advantageous for us to do that. Plus c. And whew, there we go. There we go. What an answer. What a great answer. And now, no one individual step is terribly hard, but of course we have to make sure we understand the principles. Identify that it is a trig sub. Make sure we know which trig sub we're using. Make sure we account for the dy. Make sure we know how to simplify the square root. Once we have our trig sub, think about how we actually integrate it. We have to deal with either sines or cosines, or secants and tangents, so know how to do your manipulations. Like, how do you trade a tangent squared for a secant squared, or vice versa? And then carry through the integration and be careful. Be the right amount of careful. You can do these. You can. You know, it's not magic. It's patience, persistence, and being careful. All of those are things you can do. All right, let's keep going. Using Simpson's rule with n equals 4 intervals, find an approximation for the moment with respect to the y-axis, or m sub y, of the region where we have constant density, delta equals 1, and we have x goes from 1 to 5, and y goes from 0 up to f of x, and the graph of f of x is the graph shown here, and our region has been shaded. So, okay, so we're trying to find the moment with respect to the y-axis of this region. And we're told, give your answer as a single number. All right, great. So we're using our tools, and in particular, of course, Notice this is Simpson's rule. The clue that it's Simpson's rule is the fact that they said it's Simpson's rule. Another clue, of course, is that we're after an approximation. We're not going to get an exact value, but we're going to get an approximation. Okay, so where do we start? Well, one of the things we should do is make sure we know what we're computing. So we are after this m sub y. So we say, wait, that's what we learned in our last part of the class, right? Well, yeah, but that still means we can use it here. And you might say, well, which one of these should I be ready for? Any of them. I will say volume tends to be very popular, but any of these applications can show up. So m sub y, that's our distance density measure. Okay, so let's write that down. All right, so we have m sub y. Let's see if we have enough space here. Equals integral a to b. We have distance, density, and measure is our height and our width. Okay, so that's our m sub y. Now, in our case, we have our region. We're going from 1 to 5. And we're thinking of, when we set up the m sub y, we would think of chopping things up. And we say, okay, how far are we to the y-axis? M sub y with respect to the y-axis. Well, the answer is, if you're at some arbitrary x, you're x away. What's our density? 1. What's our height? It's the function, which we don't really know what that function is. And what's our width? It's the small change in x, it's dx. Okay, so we really are saying, hey, we are after the integral of x f of x dx. That's our goal. Integrate that. Okay, so, well, we're not going to integrate it because we don't know what f is. Approximate that. Approximate that. And now we say, okay, well, let's think about what's going on. We're going to go from 1 to 5, so we're going to chop it up our 1 to 5 and split it into 4 equally sized pieces. And good news, that turns out to be very easy to do. And okay, so we're going to have at 1, 2, 3, 4, 5. Well, what's the width of one of our pieces? You have to pay attention. Sometimes it's nice, it's 1. Sometimes it's 2. Sometimes it's a half. Sometimes it's a third. Don't neglect this part. So our intervals are 1. Now, when we're doing Simpson's rule, there's a very convenient guideline here. So see the S for Simpson's. Here's the guideline. So it says, and I'm just going to copy it down from memory, delta x over 3, and then there's this pattern 1, 4, 2, 4, 1. Now, that's if you have, this is actually if you have 5 data points, but n equals 4. If you have additional points, then you just sort of keep that 4, 2, 4, 2 going through the middle. So it's 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1, right? Okay. We're not going to ask you to add a lot of numbers. But be ready to be able to add 5, maybe 7 numbers. We believe in you. We believe in your ability to add 5 to 7 numbers. You can do it. Don't worry. You can do it. Okay, so what's going on? Well, what that tells us is we're going to take delta x over 3, and in our case, delta x is 1, so it's 1/3. And now we have these coefficients. So it's 1 times what's happening at 1. Okay, so it's 1 times, and this is at 1, plus, now the next 4, and then we're going to times it by what's happening at 2, plus 2, and now again at 3, plus 4, and then we're going to times that by what's happening at 4, and then plus 1, And then we're going to times that by what's happening at 5. Okay? So we're sampling our information. So again, when we do numerical integration, it's like I'm not going to use everything about the function. I'm using information about the function at these equally spaced points where sort of like there's an underlying hypothesis that the function isn't too crazy, and most functions are not that crazy. Okay, so now we have our delta x over 3, 1 over 3. We have our coefficients 1, 4, 2, 4, 1. What goes in the boxes? The age-old question, what's in the box? What's in the box? Right? That's what we need to fill in. Now, be careful. It's not the function. Because we're integrating not f of x, but we're integrating x f of x. So that's what's going to go in those boxes. Okay, so at 1, I need to know what is 1 times f of 1. Well, we come over here. The value of f of 1 is 1. So it's 1 times 1, which is 1. Now, how about at 2? Well, we see that f of 2 is 2. So it's going to be 2 times f of 2, which is 2 times 2, which is 4. Now, 3, we have here that we are at 3. So f of 3 is 3. So when we plug in 3, we'll have 3f of 3. That's 3 times 3, that's 9. What about f of 4? Well, that's up here, that's 5. Oh, okay. So f of 4 is 5. So we plug in 4 times f of 4. 4 times 5. 4 times 5 is 20. And now, here, we have that f of 5 is 4. So when we plug in x equals 5, 5 times f of 5, 5 times 4 is also 20. All right. So we have our approximation is 1/3. Well, let's start simplifying. 1 times 1 is 1. 4 times 4, 16. 2 times 9, 18. 4 times 20, 80. 1 times 20, 20. Well, 80 plus 20 is going to be really easy to work with. That's 100. 16 plus 1 is 17. Plus 18, that makes it makes 35. Plus 100 makes 135. So we get 1/3 times 135. And then we say, well, can you divide 3 into 135? You can. And if you carry that out, that turns out to be 45. So that's the answer. Now you might say, why didn't we stop there? Did you notice that there was an instruction? Give your answer as a single number. We actually had to add the numbers up. And so if it says give your answer as a single number, you can't stop before it's a single number. And so, all right, 45. Is that reasonable? Actually, it is, yeah. You can kind of eyeball it and guess somewhere in the ballpark of 45. Let me sort of reason why that might be true. First off, you can say, well, look, the moment is if you knew where the center of mass was, right, for this shape, then say, okay, take the mass, total mass, and imagine it was centered at just a single point. And then just what's the moment if that were the case? Well, you can count some squares. You get 1, 2, 3, 4, 5, 6, 7 and a half, 8, 9, 10, 11, 12, 13. Well, let's say the area is about 13. Okay, where's the center of mass? Well, it's probably somewhere around 3.5. And somewhere around here. So we would say, well, we want something around 3.5 times 13. And 3.5 times 13 is about 39 plus is that? 6.5? 45.5? Yeah, 45 is pretty reasonable. All right. Well, cool. Cool. Do we know, is that the answer exactly? No, but we were after an approximation. So this is kind of fun because it combines applications with, of course, Simpson's rule. And so, yeah, be ready for applications. You should anticipate there being an application. Be ready for numerical integration. You should anticipate that you're going to have to do some kind of numerical integration. These are important ideas. All right, we're almost there. The end is near. Let's finish it up. Evaluate the improper integral. 1 to infinity, 2 plus 6x over x plus 1 times x squared plus 1 dx. For full credit, include appropriate limits in your answer. Ooh, okay, all right. So we got some work cut out for us. Now, we know it's improper because it tells us it is. And when you deal with improper, limits come into play. That's right. So we're going to deal with limits, and we'll get to that in a few minutes. Now, one thing we could ask, is this even a hard question? Maybe it blows up. Do we expect it to converge? Because we can channel the same kind of energy when we were dealing with number 6. And we say, well, if we think about it, upstairs the rate of growth is like x. Downstairs it's like x cubed. So it's kind of like 1 over x squared. Oh, that converges. So this should converge. All right, so we say, okay, it's going to converge. Now we just have to figure out what it converges to. All right, well, here we go. What's the technique that we need here? Well, we see polynomial upstairs, polynomial downstairs. It's going to be partial fractions. Now, one way I sometimes approach improper integrals is I say, I'm going to do it in sort of 2 stages. So I'll do it here. Stage 1 is do it as an indefinite integral. Then stage 2, do the definite integral where it's improper. So when I do it as an indefinite integral, then I don't even have to think about improperness, and that just sort of helps move that sort of distraction to the side. So doing that, let's say I want to find the integral of 2 plus 6x, divide that by x plus 1 times x squared plus 1 dx. All right, that's the integral we're after. Now, we're going to spend most of our time doing this integral by doing algebra. So let's do our algebra. We say, all right, well, really, 2 plus 6x divide by x plus 1 times x squared plus 1. Well, we have our pieces, x plus 1, x squared plus 1. Now, you might say, Steve, you forgot to check the degrees. Well, we kind of already did when we talked about convergence, but okay, quickly. Upstairs, degree 1, downstairs is degree 3. We don't need to do long division. All right, so back to our regularly scheduled problem. The x plus 1 tells us that we have something over x plus 1. And the x squared plus 1 is we have something over x squared plus 1. We don't have any extra powers. It's not like x plus 1 cubed, so that's going to be nice. Now, on top of the x plus 1, because x plus 1 is linear, we're going to have one unknown. So we have a constant to be solved. The x squared plus 1 is an example of what's called an irreducible quadratic. So upstairs, we're going to have 2 unknowns, the bx plus c. So now, with that, we sort of do a quick sanity check. We have 3 unknowns, good. Degree 3 downstairs, good. All right, and we're going to clear our denominators. So if we carry through that computation, multiply everything by your original denominator, x plus 1, x squared plus 1. We get that 2 plus 6x is equal to a. The x plus 1's cancel, so we get x squared plus 1 plus bx plus c times x plus 1. All right, well, can we make some good choices here? Are there some values where we're going to get things canceling? I think there are. All right, so what are some good choices that can be made here? Well, see how we have an x plus 1? So let's start with that good choice. X equals negative 1. 2 minus 6. is negative 4 equals a, negative 1 squared is 1, plus 1 is 2. And then bx plus c, well, it's minus b plus c times 0. That goes away. So this tells us then we can solve a is negative 2. Now, is there any other good choice? Well, notice how we have a b times x. 0 is a good choice. So, all right, we'll throw in a 0. Why not? X equals 0. 2 plus 0, 2, is equal to a times 1. But we know what a is, so that's negative 2, plus b times 0 plus c, which is c times 1. Okay, oh, hey, look, I can add 2. That tells us that c is 4. And now you're like, haha, you're out of good choices, Steve. Yeah, but I can just make any choice now. Any choice is a choice, and that gives us relationships. It's just good choices are ones where we have very few letters involved. And but any value for x gives us a relationship. So plug in 1. 2 plus 6 is 8 equals a times 2, but we know what a is. That's negative 2, so a times 2 is negative 4, plus, then we have b plus c, but c is 4, so that's b plus 4, and then 1 plus 1 is 2. All right, well, that says we have b times 2 is 2b, or is it not 2b? Well, yeah, because there's negative 4 plus 8, which is plus 4. So 2b is 4, or b is 2. All right, so that's good. We've actually done all the hard work, and be careful to make sure you get every value back where it should be. So a is negative 2, b is positive 2, and c is a positive 4, which tells us that our indefinite integral, because we're doing an indefinite integral right now, becomes minus 2 over x plus 1 plus 2x plus 4 over x squared plus 1 dx, which we can pull this a little bit further apart. So that's minus 2 over x plus 1 plus 2x over x squared plus 1 plus 4 over x squared plus 1. And so here we're taking advantage in that we have a good plus sign. A good plus sign in that it's a plus sign where we can break things up. So it's upstairs, it's not inside a square root or anything like that. Now, term by term, we integrate. So we'd have minus 2 log x plus 1. Here, x squared plus 1 downstairs, 2x upstairs. You can hopefully do this in your head, and it's one that we see a lot. Think about what's going on here. If channel your inner, I want to make a substitution. If u were x squared plus 1, du would be 2x dx. So it's like you have u downstairs, du upstairs, log u. Or it's log of x squared plus 1. In general, if you ever have function downstairs, derivative upstairs, then you say, oh, well, that's log of function. Now, 4 over x squared plus 1, classic. Come on. We had to mention it at some point, and it's just kind of sad that we waited so long. Arctangent. Got to have it in there. Got to have it in there. All right. Now, we are done with the integration, but I want to do one more thing. I want to work with these logs, and can we put them together? So we say, well, yeah, absolutely. We can write it as a single log, because what happens? Well, the things that are being added are in the numerator, and so I have a plus log x squared plus 1, so there's an x squared plus 1 upstairs. Being subtracted means denominator, so there's x plus 1 downstairs, but notice there's a 2. How do you handle that 2? Well, you take that 2, and it's going to come in as an exponent. So we really have downstairs x plus 1 squared. All right, plus 4 arctan x. Okay, so that finishes us with sort of part A. It's not explicitly part A, but sometimes it's convenient to say, let me, instead of thinking about it as an improper integral, let's think about it as an indefinite integral. Then we're going to switch to improperness. Now, as we're switching to improperness, how is this an improper integral? What's making it improper? The only issue is that infinity. There's no other problems. It's not going to blow up in between 1 to infinity. The asymptotes aren't there. I mean, yes, sure, there's an asymptote at -1, but that's far away. It's not our problem. We just have one problem, that single infinity. So we say, look, for full credit, we're going to include appropriate limits, and we're going for full credit. We want that full credit. So we say what? Well, this is the limit as, all right, let's be a little bit careful here. So the integral from 1 to infinity of 2 plus 6x over x plus 1 times x squared plus 1 dx is the limit as b goes to infinity, 1 to b of 2 plus 6x divided by x plus 1 times x squared plus 1. Right? We need to put that limit in there. Now we say, but wait, we know how to integrate this, so we can integrate and evaluate. So this is our limit as b goes to infinity of log x squared plus 1 over x plus 1 squared. Sorry, my handwriting's really bad there, but we have that for reference. Plus 4 arctangent of x. Evaluate that from 1 to b. Okay, so this becomes our limit as b goes to infinity of, now plug in b. And I'm going to break it up into a couple pieces. Log of b squared plus 1 over b plus 1 squared. And then I can say plus, there's this other part, limit as b goes to infinity, of 4 arctangent of x. All right, so that's plug in b. Subtract, plug in 1. Okay, 1 plus 1 is 2. 1 plus 1 is also 2, but it's 2 squared. So it's minus log 2 over 4. And then here, our tangent of 1 is what? Well, we can actually figure it out. It's from the formula sheet. Because our tangent of pi over 4 is 1. So our tangent of 1 is pi over 4. So plus 4 times pi over 4. Okay. All right. Good. Good. Now, we're going to unravel all of this. Let's start with this piece. B squared plus 1 over b plus 1 squared. It's polynomial over polynomial, same degree over same degree. So look at the leading terms. Upstairs is b squared, downstairs is b squared. So this is going to get close to 1. On the inside, log of 1 is going to do what? It's going to go to 0. Okay, so this first limit goes to 0. How about here? Arctangent. Well, if you know tangent, there's these vertical asymptotes, and then you have your function. So here's tangent. So arctangent, those vertical asymptotes become horizontal asymptotes. And in particular, you have a pi over 2. And so what happens is that as arctangent goes to infinity, so as we're moving, we're going to approach the asymptote of pi over 2. So this goes to pi over 2, just the arctangent, but times it by 4, then the whole thing goes to 2 pi. And so now we've done our evaluation with our limits, so we can clean it up. So we have 0 from that term, 2 pi from this next term. Now, log of 2 over 4, that's really log of a half. And log of a half is minus log 2. Minus minus makes a plus log 2. Then we have minus 4 times pi over 4. Well, that's minus pi, right, because the 4's cancel. The 2 pi minus pi leaves us with pi. Then we have plus natural log 2. So our answer is pi plus log 2. Whew! All right, good. Ha-ha! We made it. We got to the end. All right, any comments to make on this one? Yeah, let's be clear. When they make a big deal of it being improper, you better put in this limit because they're going to check for that. That's going to be part of the answer. Know how to deal with limits. Sometimes you have asymptotes, like here you have arctangent. Sometimes you have like polynomial over polynomial, then you say, okay, what's happening? If you have low degree over polynomial over high degree polynomial, goes to 0. If you have polynomials of the same degree, look at leading coefficients. Because what's going to happen is all the other terms are going to be inconsequential. But yeah, just remember to use limits, carry them out, and you'll be okay. Now, this brings us to the end of our practice, and you might be looking at the clock and saying, it's supposed to be a 75-minute test, Steve. You took a lot longer than 75 minutes. Okay, so I agree, I did. But I was trying to use the review as more than review. I was trying to explain a lot of ideas. And in the process, I chose some problems which I think are a little bit harder than what you should expect to see on the exam. Because it's good to do hard problems. Hard problems prepare us for anything that we might see. So make sure you practice. This is not the test. It's practice. And the problems are a little bit harder than what you'll see on the test. Or at the very least, they're definitely different. But now, if you are preparing, you'll be ready. You can do it. And I know that you're working hard, and I appreciate you taking the time to go through and do these problems with me, and I hope that they're helping. I believe in you. You can do this. You can get past this test, you can get past this class, and you can succeed. Keep working. You'll be fine. Go into that test. Breathe in. Breathe out. You're gonna do great. And then let's see each other again for the next exam. All right. Bye.